Okay. So we were writing for our homework. We were writing well, let's talk about the paper quickly first, and then we'll do the code. A mental warm up report. Discussing the role of binary, octal, decimal, and hexadecimal in computing. At the very least, cover the following topics. Why do we need so many different ways to represent data? Efficiency related to working with different number bases, and when and why might we use a base greater than 16? Okay, so let's cover those in order. Why do we need so many different ways to represent data? What's the punchline there? Human beings, we like decimal because of 5 fingers, 5 toes, right? Well, on each hand. Why octal? Why binary? Why hexadecimal? Why do they exist? Was it just because somebody decided they needed to be different? So what is it? You guys had to squeeze 3 to 5 pages out of this. So hopefully we get something.
They're used based on their requirements.
Okay. What kind of requirements would benefit from a higher or a lower base?
So the higher, some I mean, help you to save some space, some memory.
Okay. So maybe we have different ways of representing data for memory purposes. So the larger the number we have to store, the higher the base we might want to use to store it, right? So for instance, if we take the number 2000, well, 2000 is probably, pick some random number in the 2000s, 2331, okay? And we looked at that number in binary, it's going to be a whole bunch of zeros and ones, right? We look at an octal, well, it's going to be maybe a 4-digit, maybe a 5-digit number, probably a 4-digit number still, but something, not hugely different than decimal. Decimal, it's a 4-digit. Once you get into hexadecimal, now you're able to represent large numbers in a much smaller footprint. Okay, so certainly memory plays a major role in this. So does that mean that before we had computers, we didn't have different bases? Did we care about memory before that? So if we go back to 1850, I very specifically picked that exact year for no reason whatsoever. If we go back to 1850, well before computers existed, right? Okay. Did these alternate bases still exist? I mean, people knew how to count back then, right? So we had picked decimal. So why did binary exist then, or octal, or hexadecimal? What did they use it for then?
Some historical, they use for example, for 24 hours, they use the base 24.
Okay. Gotcha. For a very specific problem, they use base 24. Okay. But at some point, somebody decided, okay, well, we're gonna, here's how numbers work. Here's how addition works, and here's how a base works. And we decided that decimal is what we use because it's convenient for us, because it's easy for us to count on our fingers, right? So that's the rationale behind decimal, correct? Human beings, it's easy for us to learn how to count with our hands. Okay? So, generally speaking, why did we need multiple bases in 1850? Or did we? So you gave an example of one reason, one solution to a problem they used a different base for, but why did we need different bases back then? Or did the use of multiple bases not really become popularized until we had computers? The different bases always existed, correct? Because it's not like somebody just made it up. That's how math works, correct? All right. So, whenever somebody made the counting system and we started counting stuff, it just happens to be that counting system is pretty universal, and depending on how you're doing your counting, data representation can make a difference. Did we really start thinking about data representation until computers? What did we find in our research? Nada? Nothing? What about efficiency related to different number bases? Is there a trade-off? You already mentioned there's a footprint efficiency to represent large numbers in high bases, right? A base 16 representation of a gigantic number will have a smaller footprint than the base 2 representation of the same number, same decimal number. They seriously still have this computer on, just rebooting for 3 weeks? Are you serious? And yes, you are learning IT from us. Okay. So there is an efficiency in terms of footprint, but what about speed? What about the other direction? So is storing things in hexadecimal format, certainly that's more compact. Will fit into your overhead storage on the airplane, right? But what about working with those numbers? Is there an efficiency benefit to working with numbers in smaller bases versus higher bases? A very talkative group tonight. It's been one of those weeks. Why do we use binary? It seems like binary is horrifically inefficient on all sorts of levels, right? You represent relatively small pieces of information in very verbose ways with a bunch of zeros and ones, correct? Like, why would you ever store, the number 2,328 as a binary number? Because it takes up so much room, right? So why would we ever do it? What's the point of binary?
It's using digital because of its straightforward implementation.
Okay, so binary actually has a very high performance when it's used for a specific application, that is the digital logic application. Zeros or ones, on or off. That's digital logic, right? Okay, so from a human being's perspective, binary is relatively inefficient. But from a computer's perspective, binary is about as smooth as it gets. In fact, working with something outside of binary actually then becomes more difficult because it has to then convert it down to something it can deal with digitally. So this kind of falls into play with this idea that human beings like characters. Computers like numbers. So that's why we have the Unicode character set. Human beings like base 10. We like the decimal number system. Computers don't. So computers let us use the decimal number system, and under the hood, it stores things in the way that makes the most sense for the computer. So our entire interaction as we're dealing with computers deals with this mapping between what is easiest for human beings and what is easiest for the computer. Even programming languages. It would be ideal for computers if we just gave them the step-by-step, one-to-one ratio instructions that the CPU directly understands. We don't speak that language. Okay, we don't talk directly to CPUs. In fact, we're so lazy, we don't even talk directly to the assemblers that do a one-to-one map to the CPU. We don't like low-level languages either. We talked about that the first week. 3 kinds of languages. There's machine language, low-level languages, high-level languages. So machine language, that's what the CPU is actually talking. Low-level language is a language that seems kind of sort of English-like, and every line of code you write maps to exactly one instruction in machine code. Well, we don't like that either. Yeah, it's English-like, but not good enough. We like high-level languages where we can write one line of code and have it represent a lot of crap, right? So our whole relationship with computers, human beings and computers, is a very strained relationship. Human beings demand convenience, and human beings demand performance at the same time, right? We want our computers to be fast, but we don't want to have to work hard for it to do that stuff. Okay, so there's all this mapping that goes on in between. And the number systems are very similar to that. When a human being is dealing with a computer, we're dealing with it in base 10, right? That's how we interact. We interact in base 10 numbers. If we're talking about the memory subsystem of a computer, a lot of times memory addresses are stored as hexadecimal numbers. In the future, it might be larger than base 16. We might get up to base 24 or base 30 or base 36, whatever, as memory gets bigger and bigger and bigger, right? We actually saw this not that long ago. So let's go back to when Windows 95 first came out, so probably 1996 or so. Back then, a big hard drive was considered like 1 gigabyte. 1 gigabyte was considered a really big hard drive back then. Now 1 gigabyte we use as like a coaster. Right? we don't use those. But then bigger and bigger hard drives started coming out, but we had an issue. For instance, you would go out and you would get a 6 gigabyte hard drive. You bring it home, put it in your Windows 95 machine. You'd have to partition that into 3 separate partitions. You'd have 3 2 gigabyte partitions. Why? The largest single partition that could be in your computer was 2 gigabytes. Even though you had a physical drive that was 6 gigabytes, each partition had a maximum size of, it was actually 2.1 gigabytes, because that was the maximum size a 16-bit memory management system could support because of the number size. Whoever wrote the software for Windows 95, who wrote the memory manager for it, used 16-bit numbers to represent memory. What's memory inside of a computer? Memory inside, and this is kind of segueing to what we're going to talk about today. Memory inside of a computer is a giant array. It's a collection, one bucket after another. So what they did is they took that 1 gigabyte. We went through and we chopped it up into all sort, a whole bunch of equally sized little chunks. And then we indexed each of those stuff. And this is chunk number 0, chunk number 1, chunk number 2, chunk number 3, so on and so forth. By representing memory as a 16-bit memory system, the largest, we didn't need to be able to index negative numbers, so we had to deal with unsigned 16-bit integers. That means we could reference numbers between 0 and 65,535, 2 to the 16th power. Make sense? Okay, very similar to the Unicode character set. Same space. Okay, so 0 to 65,535 was the number of unique buckets of memory that we could support. Okay, whether we're dealing with our RAM in our computers or we're dealing with our hard drives. Memory is memory. The thing that changes is the speed. Hard drives are slower than RAM. RAM is slower than L3 cache. L3 cache is slower than L2 cache. L2 cache is slower than L1 cache. L1 cache is slower than registers that live on the CPU, which is, I guess, slower than light, is what we finally get to. But memory is memory. It just comes down to speed. So the idea is, when we have a file system, so back in Windows 95 days, so this is giving some IT background dealing with these numbers. Back in the Windows 95 days, what was the popular file system if you were running Windows 95? Same popular file system for Windows 98. Same popular file system for Windows Millennium. was probably still relevant. Actually, it's still relevant today, but you wouldn't see it on your hard drives. You'd see it on your flash drives today. So if you have a jump drive, a little USB stick, you'd have the same file system on that today as you had in Windows 95, the second version of Windows 95. So it's Windows 95 Service Pack 2. What file system is that? FAT32. Before that, we had FAT16. FAT16 was in the first version of, this is File Allocation Table 16. So it's what they use to format your hard drives. Your hard drive would be formatted FAT16 or FAT32. Today, if you're running, Windows XP, Windows Vista, Windows 7, Windows 8, you're running NTFS, which is New Technology File System. This came out with Windows NT 4.0, which was alongside of Windows 95, a long time ago. Okay, so this is the newer file systems that everything runs now. But FAT16 used typically a 4 kilobyte block size, which means each chunk of memory was 4 kilobytes in size. And how many chunks of memory could we have? We could have 0 to 65,535, so 65,536. 65,536 times 4. Actually, it might have been 8. We'll see. We'll know here pretty quick. 65,535 times 4 is that many kilobytes divided by 1,024. Well, maybe it was bigger than that. Thirty-two kilobyte blocks. Okay, so a FAT16 system used 32 kilobyte blocks, which means every bucket of your hard drive, every subsection of your hard drive, they're called frames, hold 32 kilobytes of data. So the smallest piece of memory you can hold on your hard drive is 32 kilobytes. Okay, this is a performance decision. Otherwise, if you only were allowed to hold 1 bit in your hard drive, first of all, you'd have to have way more than a 16 bit file system. You'd have to have probably a 128-bit file system to even hold a reasonable amount of data. But regardless, computers or hard drives are mechanical, right? So in order to put together a Word file, if you had to zip to 300 different locations on your hard drive just to put together all the bits that make up your Word file, that would be slow, correct? Efficient in terms of memory footprint, but performance slow. So our block size was 32 kilobytes. So every bucket of our hard drive was 32 kilobytes. Well, if you do out the math, 32 kilobytes times 65,535, the largest hard drive you can have is about 2 gigabytes. So even if your hard drive physically could store 6 gigabytes, you could only partition it into a 2.1 gigabyte file system because that's all the number system allowed you to address. You could have 3 of those, because you'd have a different address table for each of those 3 partitions. Does that kind of make sense? All right. Well, then we went to FAT32. FAT32 lets us have much larger file systems. But there's actually a limitation to a single file size on FAT32. So another piece of trivia information. How many of you have a jump drive or an external USB hard drive? Okay. All of those, unless you otherwise formatted it, will be FAT32. Out of the box, they're all FAT32 file systems. How many of you have ever tried to put a single file onto one of those devices that's larger than 4 gigabytes? Ever once? Well, I'll tell you what will happen. If you ever try to put a file onto one of those things that's larger than 4 gigabytes in a single file, it will tell you that your disk is out of space. So you have this 250 gigabyte external USB hard drive that's empty. Nothing's on it. You're trying to put a single 4 gigabyte file on there. Well, 4 gigabytes, less than 250 gigabytes, right? We could even make this more obscene. You go out to Best Buy and you buy the new 3 terabyte Seagate external hard drive. We're trying to put a 4 gigabyte file onto a 3 terabyte hard drive. It will tell you, sorry, not enough space in your hard drive. Oh, there's enough space, right? Problem is, because it's a FAT32 file system, any individual file can't be larger than 4 gigabytes. For the same reason we're talking about here. So if you need to store files on your USB sticks or your external USB drives that are larger than 4 gigabytes, go in and format it either NTFS, or if you're a Mac user, format it as a Mac OS file system, which is a Unix file system, HFS. And they can store larger files. But then don't try to open them on, for instance, if you have a USB stick and you format it NTFS, you won't be able to read it on a Mac. If you have a UPS stick, a USB stick, I don't know what I said the first time, UPS probably, whatever. Good carrier. I recommend them highly. If you have a USB stick and you're on a Mac and you format it Mac OS, put it into a Windows machine and won't be able to read it. So FAT32 is compatible across both. That's why they come that way. Make sense?